first boundary condition, this boundary condition, right? When y go to infinity, y approach to 0, y equal to 0, right? Y equal to 0, this should be, the W should be equal to capital U, okay? Okay? So this is our what? This is our this is our solution for this solution form. Solution for the W function of y should be look like this. So our capital U over our U over U will be equal to what? Original we have defined like this: Wy times this potential int and take a real part. So finally we can apply. We already have the Wy function already. So this is Wy function. So our capital U small U over capital U is this is our solution form. Okay, we already divide our U to our U here. So this is become and so we can find out this is one is the real part, one is the imaginary part, and real part give you its potential function. Imaginary part give you the sine cosine function, right? And sine cosine function, since we take the what? We take a real part. So real part is only the cosine function. So this is finally we have this cosine function here. So if you extend this is a real part, this is imaginary part, right? And imaginary part give you the cosine plus I sine, right? And then take a real part, only cosine. So this is the cosine we have. Okay, so finally we have this solution form. Okay, this is solution form. This is so we have U times this, right? Is our amplitude because this is a time domain, right? This is only function of y. So if you divide, U times this give you the amplitude. Okay, so amplitude will be oscillate and also decay is potentially with y because this is potential decay with y. So our capital U times this give you the amplitude. And then according to time, as you can see, cosine nt minus square root n over 2 mu y. Okay, and here is what? Here is our phase leg. Okay, so phase leg will be also changed with y. Okay, it's changed with y. Okay, so that will be give you the oscillation. Okay. And then also we can have a similar so-called like a previous penetration depth idea. We try to find the oscillation plate, how far the boundary thickness should be. When I define the boundary thickness, I mean above this boundary thickness, the flow disturbed is very small. Okay, but below that, I can see a large or the variation of velocity profile change. Okay, but above certain distance, this change is very small. Okay, and we define this is a so-called our boundary layer thickness. So we can define our boundary layer thickness. Okay, so this is called the delta, and delta is the distance from the plate at which the amplitude of the flow motion decay to its potential minus 2. So we can find out this capital U times this is our amplitude, right? And this give you its potential minus 2. This is equal to 2, right? Square root of n over 2 mu y equal to 2. So square root of n equal to 2, and I can find out this delta. Okay, so this is y is we define this at this occasion y is equal to delta. It's our boundary layer thickness, and this is our boundary layer thickness. Look like this. Okay, so as you can see here, mu is a constant, right? If you choose the one viscosity, for fluid, and the only change is the n here. N is what? N is a frequency. Okay, n is frequency mean what? If you oscillate very slowly, period, that means once per second, right? 1 hertz. Okay, and our penetration depth will be what? Will be very large. Okay, if n is small, this delta will be large. If n is very fast, that means this oscillation very fast, like this. The delta will be very small. So here is you can see here. Okay, delta is proportional to 1 over square root n. Okay, So the oscillation faster, your penetration depth of boundary layer thickness will be smaller. Okay? So this boundary layer thickness will be delta equal to 2 square root this function. And n is what? N is 1 over time, right? So 1 over n is a time. So it is proportional square root of mu t. Similar idea we have discussed before. Okay, this is also viscous effect, and how far this viscous can transfer. Okay, the thickness delta will be proportional to square root of mu t because n is 1 over t. Okay. Okay. And here we have the one. Okay. I think I try to find out one. Okay. One of the solutions here maybe. Stokey boundary layer, right? So this is I find out one of the, okay, this is a solution, okay? You can choose, okay? You can choose your amplitude, okay? Amplitude means here is amplitude, right? How big is that? I fix amplitude. I change our oscillation frequency, okay? And this is the time, okay? So you can see that I change the time, okay? And then if I choose the very slow, n is small, okay? N is small here, okay? N is small here, and I change with time. As you can see, the variation like this. If I oscillate, okay, like this, so as you can see, this n is small, okay? The penetration of boundary layer thickness maybe at this occasion, okay? If I change n is a bigger value, okay? That means n is large, okay? And this, as you can see, what happened here, okay? If I oscillate, the velocity profile will look like this. So penetration depth of boundary layer thickness only here. So which is far? Oscillation faster, smaller, right? Oscillation slower, okay, penetrate more, okay? 所以你可以看到，如果说我把这个 n frequency 调低，它就比较，它传的就比较远，对不对？它的 boundary layer thickness 就比较远，有没有？左右在晃动的时候 ，when you have oscillation on the boundary, your flow will look like this. Okay, and if I choose n bigger, okay, you can see the, okay. Okay, so you can see the difference between the discussion here. Okay, when n is a large number and n is small number, you have a different, okay, you have a different boundary layer thickness here. Okay, so that will be give you. Okay, I think, okay, and the next. We'll go to another physical problem, and this physical problem is very useful. Okay, if you study the biomechanics, biofluid mechanics, okay, like our heart, right? 像我们的心脏 our heart is a pulsating, right? It's a squeeze and the expansion squeeze, and the circulation system in our body, okay, blood vessel also this is related to this physical problem. So this physical problem called the pulsating flow. Okay, we have unsteady pressure, and try to understand what's the flow field inside. Okay, and this is very basic problem for the biofluid mechanics. Okay, 如果你去 okay, so again, we simplify our problem is only between two parallel plates. Okay, so since along the plate we didn't change the distance between two plates, so partial v partial x equal to 0. That means at any x location, all the velocity profile should be the same. So we can reduce we don't have any vertical velocity component. We only have a u component. We don't have any. And our Gaussian equation for this case, okay, is different from the Stokey problem. Stokey problem don't have a pressure change, right? But for this physical problem, the driving force is our pressure. Okay, so we have unsteady pressure and try to drive the flow between two parallel plate. Okay, 我们有一个 unsteady 的压力波。Okay, and so this is unsteady pressure. Okay, partial P partial S is a Px times cosine Nt, right? This is a Px is a constant, so cosine Nt change with time. So our pressure gradient change with time. Okay, so this term here is our unsteady. So when we have an unsteady pressure source and we try to understand what's the flow field for this. Okay, again, okay, we try, this is a cosine function, right? So boundary condition, okay, for this physical problem, we have the two parallel plate, and on the two parallel plate, on the bottom wall minus A, and upper wall y equal to positive A. At these two wall location, our velocity should be reduced to non-steady boundary condition. Okay, 所以这地方我们这个主要是有两个墙壁。Okay, we have two parallel plate. Okay, so we have the two floor, two parallel plate. And this is our x, this is our y, and this is the y equal to positive A here. This is y equal to minus A here. Okay. So this is the so we have the dp dx is a cosine function, dx cosine function, cosine Nt. So this we're driving our flow forward and look like this, and then reduce, right? And then oscillation like this. Okay. Sometimes push forward and then negative pressure. Okay. And this is maybe the case. Okay. Okay. So here we have this carbon equation with these two boundary conditions, y equal to positive negative A, our velocity should be equal to 0 due to the non-steady boundary condition. Okay, so here, okay, first we would like to find out, okay, the solution form for this. Since, again, our pressure is a cosine function, right? So we also can separate our flow field, okay, by using the separation of variable like this, okay? And however, since our velocity should be also sine or cosine function, so we're using the exponential INT, and then this will be composed by the cosine plus I sine, right? And then we take a real part because this is cosine Nt here, okay? So we have this solution form, okay? And this solution form, by substituting into this, okay, we try to find out, this is a carbon equation reduced to this, okay, very similar to previous, okay. So we try to find out this W function of Y, okay, and W function of Y will be like this. The carbon equation for this W function should look like this. If you substitute this into here, you take a first derivative with time, and the second derivative with y, and then try to equal this, it will be reduced to this. So our boundary condition, again, our boundary condition W at y equal to 0, at y equal to positive negative A should be equal to 0. This should be not incorrect, okay, this should be Wy here, okay, should be equal to 0 instead of 0. This is not y equal to 0. 所以这个地方错掉了，你把它改一下，这边写 wy， 然后这个 y 等于这个的时候才等于0。Okay, so should be correct as this is w a function of y instead of 0 here. Okay, try to correct in your lecture note. Okay, so what's this physical problem we have? What's this physical problem we have? We have mu d squared w dy squared. Right? Minus in w equal to what? Equal to 1 over log px. Because, okay, I just try to rearrange this equation. And what this equation look like to you? This is also the second order differential equation, right? Because this is second order. Okay? And you have learned this, right? A, B, C equal to D, right? You have learned this. You have learned this how to solve this problem before. This is all constant. 你这在公数有学过，对不对 ？Okay, so look like this. This is we don't have this term. A is equal to this, C is equal to this, and D is equal to this. Right? And we call this kind of OD is what? Linear OD, but what? Inhomogeneous OD, right? What's the inhomogeneous mean? Our D is not equal to 0, right? So this is inhomogeneous. Okay? However, solution form for this should be start from the homogeneous plus a particular solution. Okay? I don't really understand what I mean. Okay? 在公数里面，我们这个叫做 OK， 这边有一个常数，对不对？所以这个常数不等于0，我们就称它 inhomogeneous OD。Okay, and here mathematical problem. I think you have to solve by yourself. Okay, and I will put on the homework. Okay, for today. So today we have a homework. Okay, and this is one of homework. We try to from here based on this and try to derive this equation solution form. Okay, by yourself. Okay, 你回去找找看看。回去把你的工程数学再拿出来，给看看你会不会解这个问题到这里。So here is a solution, okay, for this linear ODE with this boundary condition, and we can find our solution form look like this. Okay, this is. Okay, so we try to study this. This is a W, right? And this we already know this W function, and our U velocity profile will be W times its potential INT and take a real part. Okay, so that's our final solution form will look like this. Okay, like this. Because we're just using this. Okay, this is W. This is W. W here. And try to, using this, give you the U over T is equal to this. Okay, that's a solution form you should have. Okay, and here we have the two, okay, discussion here. Okay. And discussion here is, as you can see here, n over 2 mu y. Okay, here you can find out this term here. What's n? N is the frequency, right? If you see this n 2 mu square root y here, right? So I try to clarify our a here. Maybe I use a to be more easy. A is a constant, right? And it's what? It's equal to n(a) squared, right? 2 mu, because this is a is into the square root, we got a squared. Right? And what's this? N is what? N is 1 over time, right? And we can write down the a, and this is the a, and divide by 2 mu. This is what? A divided by t is the velocity, right? So this is velocity. 1 of velocity. Okay. For example, I'm using the v velocity. Okay, this is the times a divided by mu. What's this? We can define so-called what's the mu? We have the mu sample is rho u a times mu, right? And also can be written as u a over mu, right? That's the mu sample definition. Now that what's a non-dimensional parameter of real sample. Okay, so here is the real sample. Velocity times, okay, this is velocity. We're using the u. Velocity times a divided by mu. Okay, so we can define this as a real, similar to like real sample, it's a non-dimensional parameter. So a squared n divided by 2 mu here. So this term here, this term here is can be defined as a real sample. So Rn is a real sample. Okay. So if you this term here is a small, much less than 1. Okay. This is a hypercosine function. Okay, and this is a hypercosine function. So this function here, we just copy this function here. As you can see, cosine function by Taylor expansion, okay, is equal to 1 plus x squared over 2 factor. Okay, and this is a Taylor expansion. 给你把它级数展开，就这样。And since x is what? X is this value, right? Since our x value here is very small value because the real sample is very small. Okay, so the factor x squared, x is a very small number, and x squared even smaller, right? And x to the fourth order even smaller. So we can have what? We can have the leading order 1 plus this, 1 plus this. So this is leading order. Okay, the rest we can neglect. Okay, so we're using this Taylor expansion based on this Lorentz number. Okay, I can simplify this hypercosine function to this, and also this on the denominator we have this. Okay, similar like this. Okay, and here this is a very small number, right? And this is a very small, and this is a 1 plus okay, another 1 plus is proportional to 1 minus okay, this is not smaller. Okay, so we also apply this. Okay, 1 plus a small number. Okay, in the denominator. Okay, 1 over this will be equal to what? Will be equal to 1 minus this. So I have the 2 terms, right? And I multiply these 2 terms. Okay, also finding the leading term. What's the leading term? 1 times 1 give you the 1, right? And this 1 times this give you, okay, y squared. And this 1 times this give you another term. So I only take these 3 terms because if you times this, if you this term, okay, multiply by this term, this is a small number. Multiply a small number, it's even smaller. Okay, so should be neglected. So I only choose the first 3 terms. Okay, this one multiply 1, and this term multiply 1, and this term multiply 1, and summarize will give you this. Okay, so for the very small Reynolds number, I have this relationship. Okay, for this function here, if you substitute this into here, 1 minus this function, 1 minus this function, 1 minus this 1 is cancelled. So I have this. So if you go our W, okay, our WUT is the real part of this. Okay, this will just copy. Okay, and then take 1 minus this, 1 minus this, give you this. Okay, give you this. And if you go, okay, if you rearrange this equation, as you can see here, this is our px is a partial p partial x cosine function, right? So px times cosine nt gives you the partial p partial x. If you compare with the, okay, compare with the previous, okay, with a steady state pipe flow, this is steady state pipe flow. Okay, it looks like similar, right? Because partial p partial x. This is only the divide by a squared take out, and 1 over r squared over a is 1 over r. So here is very similar. Okay, for the small Reynolds number, as you can see here, our velocity profile will be very similar to what? To the steady state pipe flow. So we call this is a quasi-steady. Okay, and the pressure turn and the velocity turn is in phase. In phase means if I have a pressure increase, I have the velocity increase. So here it looks like this. This is a pressure oscillation, and pressure is a positive. I have a positive flow, and pressure is negative. I have reverse flow. So that's an in phase. Okay. So if you plot the velocity profile with this pressure wave, that will be in phase. I have a positive pressure, and this is positive, negative pressure, reverse pressure gradient. I have reverse flow. Okay, so that will be in phase with your pressure. Okay, 所以这个地方我们会 we can have this flow is in phase with the pressure gradient. Okay. Okay, I think I've run out my time. Okay, we will discuss this. Okay. Next week. Okay, and we have one homework today, right? So you should submit your homework here. Okay, if you have finished your homework.